Yeah, hello everyone. Welcome to SDOET Times. This week is the third week, and I'm going to introduce the generalized edited model. So I think you have learned about the multiple linear regression on Tuesday, and here is the regressions. Its equation will be like these equations, and we know about the relationship between the response and the predictor is linear. And in generalized editing model, it can allow to fit a nonlinear function for each predictor. So for example, we fit the f1 function to for the s1, f2 for s2, and so on. So it also called a additive model because we fit a separate fj for each xj and add them together. So we call this is a general editing model. For example, if you use the f function is the linear terms, and that will become the multiple linear regression. So in the other word, linear regression is a special case of the generalized edited model. It depends on the f function, what do you choose. And next thing is how do we define these f functions. So the one way to define it is use the basis functions. We can define a family of the basis function like this, and B0 to BQ are basis functions. And we also know the B0 is equal to 1 because the list is intersect. And all of the list basis function are fixed and known. And beta 0 to beta Q are coefficients. And you can think about this is a standard linear model with the predictor with the B1 to B2 to BQ. And then I will give some express some popular regression model to how do we rewrite to into the base function. So the first example will be the polynomial regressions. First one is the simple linear regressions. You have these equations y equals to beta 0 plus beta 1x. And then so we can assign the basis function b0 is equal to 1, b1 is equal to x. And then you can express this equation to into the basis function. And the similar to the quadratic regressions, we have the quadratic equation function like this. And we can assign b0 equal to 1, b1 equal to x, and b2 equal to s squared. So on, if you have a polynomial regression with the p degree freedoms, we can assign each basis function as like this. B0 equal 1, which is the intercept, and B1 is the x, is linear terms, and B2 is the square terms, and BP will be the s to the power of the p. And then the second example will be the piecewise constants. And piecewise constant function will be like this figure show that it's also called a step functions. Each C1 to CK is the indicator functions, and it will return 1 if the condition is true. And which means that we have the cut point will be the C1 to CK. And then we can represent this equation into the basis function with the B0 is the same is 1, and Bj will be indicator functions until to Bk. And the next thing is about since the piecewise constant is divided the several region into the whole range of the data. So, and then we have the piecewise qubit polynomial. So you can define a set of the nuts, which is Kasi1 to Kasi and then they will divide we have the k plus 1 regions, and each region will fit the qubit polynomial, which is in this equations, and then we also need to measure their continuous. So as you can see these figures, if we in this case we have the two knots, which is two breakpoint, and they have divided to the three regions. This is the first one, second one, and third one, and each region will fit the qubit polynomial. So at first it will be discontinuous, and because we need to make sure this green line have two continuous, so we need to set up the constraint. For example, continuous will be this function will be equal at each breakpoint. And then the first derivative and second derivative will also be to continuous. So you need to let this function, this constraint. And then therefore, this represent the green line, which is we call the regression spline. So this is a qubit spline with the k-knots. It can be represented like this equation. It starts from the qubit polynomial, the first four terms, and then each knot has their truncated power basis functions. Then we have the k knots, C1, C2, until to Ck. So in qubit spline, we have the basis function that can be represented like this. And also, because you can also change if you wanna change the qubits, we can, instead of the qubits, we can use the quadratic, and it's very similar to qubit spline. You just set up this is the quadratic function, quadratic polynomial, and each has the quadratic term, and it was similar like this qubit spline. They are very similar. And the next thing is about the natural spline. And natural spline is based on the qubit spline and adds additional constraints. So it allows the linearly beyond the boundary knots. For example, this is in these figures we have four knots, and in the first region and the fourth regions we let them be linear. So you can see the red line is the natural spline, which is here. There will be linear instead of the qubit spline. It fit the qubit polynomial. And in this way, we have another 4 degree freedom. So because we let this region is a linear term. So original we have a qubit spline. We have the 4 degree freedom. So right now it's linear. So we have the free 2 degree freedom in this region and this region. So it totally have the 4 degree freedom. So based on this qubit spline, this is the qubit spline functions, and based on this additional constraint, we can derive and obtain we have the beta 2 is equal to 0 and beta 3 is equal to 0, which is their square term and the qubit term will be 0, and also this term will be 0 and this. So therefore we can derive to the natural spline can be represented by the k basis function like this. B1 is 1, B2 is x, which is the linear terms, and for each k knots, we have the pk plus 2x will be represented like here. So the next thing is how to choose the number and the location of knots. So usually we put the knots at the quantile of data. For example, we can put the knots in 25, 50, 75 percentile. And then and how do you choose the number of knots? The first way is you should try the different number of knots and see if they is a best looking curve. And another way is to use the cross validations. And so in this figure show that this is for the natural spline and qubit splines, and degree freedom. So you can see the y-axis is a mean square error. So we can find that maybe in nature spline we can choose the degree freedom is almost 3. This is a better, the best way. And for the qubit spline, we maybe choose the degree freedom will be 5 in this case. So, and instead of the next thing is about talk about the smoothing splines. A smoothing spline is kind of a function that minimizes these whole equations. The first part is a loss function, and the second part is the penalty terms. So which means that if you ignore the second part, which is lambda equals 0, there will be we usually do the list in this way. G can be the any function. So it's and you can see, you can imagine that this is the residual of the sum of squares. And if you lambda is goes to the infinity, and G will be perfectly smooth. So and then how do we minimize these equations? So the minimizer is you put the natural spline with the nuts at each data point, which is you put the nuts is equal to S1, S2 to Sn. And then in this way, we have the degree freedom will be n, but somehow if your observation n is too large, it will be overfitted. So we have to define another degree freedom. We call the effective degree freedom, and then the lambda is the control the smooth spline. So when lambda increase and your effective degree freedom will decrease. And the fittest smoothing splines, this will be the present in this equation, and know that S lambda is a smoother matrix, and we can calculate the effective degree freedom is the sum of the diagonal elements of this matrix, and then we can define the smooth spline. So right now it's kind of the basis function for the different basis for different regressions, polynomial regression, qubit spline, natural spline, and smoothing splines. And so the next part I will demonstrate how the right are called to fit the list functions. So the first thing, we have the BS function, which is the B spline, basis splines, and they have the several options you can define. The first thing is the degree. It's the degree of the piecewise polynomial. The default is 3, is for the qubit spline. And you can choose the 2 is for the quadratic spline. Even you can choose the degree is equal to 1 is for the linear spline. And the distance df is the degree freedom. It's the number of the coefficient. It's different from the least degree. So you need to mention this 2 is not the same thing. So and default is null. If you put the degree freedom df is have number, they will choose the df minus degree nuts. For example, if you choose the df is equal to 6, they will choose the 6 minus 3 nuts, which is the 3 nuts in the x. And then you also can put the specific value in the nuts. And also there's the intercept, the default is false. And the next thing is the natural spline. We use the NS functions, and it's a natural spline. And we also have the intercept. The default is false, and df is the degree freedom, the number of the coefficients. Default is 1, and if you choose another number, they will choose this equation, the number of nuts. For example, df is 4. They will choose 4 minus 1 and minus 0 if your intercept is 4. And they will choose equal to the 3 nuts in this case. And also, you also can put the nuts for the specific value. And then for the smoothing spline, we can just input your predictor variable and your response and select your degree of freedom. And so how to fit the generalized editing model? We have the 3 ways you can fit this model. So the first way is use the LLM functions, and you can just use the LLM, and this is your formula. You can use the BS is the basis spline, and that's the natural spline to fit this is your formula, and you can summary and plot it. And another way is to use the GAN package. And you can download the GAN page, and there's the GAN functions, and you can similarly put the formula like this. But in this package, they use the smoothing spline. You cannot use the BS or NS in these functions. And also, this 5 and 4 is a degree of freedom. And for the third way is there's another package called NGCV package, which is the mixed GAN computation vehicle with the automatic smoothness estimation. So it has the same function, GAN function, and the same way as this way, as the same as the GAN package. And this also use the smoothing spline. But I will talk about there's some summary result have the difference. Yeah. So okay, let's go to the studios. So the first thing I will library the ISLR because I wanna load the data from the list books, and we can just library it and see the list data and attach and view the list data. So we have the different variables, year, age, and we have the weight. Like this whole data state. And then first thing, we can fit the polynomial regression with the 4 degree freedom. You can just use this way, poly function, and this is choose your degree freedoms, and you can fit it, and that will show the summary result like this. They have the estimates and adjust of squares, something like that. And you also can just type the each terms, the square terms, cubic terms, and then they will show the same results. And then so we can use this function to predictions and plot the predict model. So we use this, and we can plot like this way. They will show this is the polynomial fitted model, and the dashed line will be the confidence interval. And then so the next thing is use fit the generalized editing model with the spline. So if you want to use the spline, you need to library the splines. There's a package called splines. And then the first thing is use the BS. So at first, I choose the NAS at the sub-6 value, which is the 25, 40, and 60. And then you can choose like this, and you can see the summary results. So in this case, we have totally have the 6 coefficients. So just remember, we have the first 3 terms is the cubic polynomial. This is for the first linear term, quadratic term, and cubic terms. And the last 3 will be for each NAS, because in this case, we put the 3 NAS. So this is for each NAS. And then you can also predict the value and plot the fitted model, it was like this, very similar with the polynomial. And the second thing is instead of choose the specific value of nuts, you can choose the df is equal to 6. So let's see if the df is equal to 6, which we have the 3 nuts. It will choose the 6 minus degrees, and degree is the 3. So 6 minus 3 is a 3. So it will choose the 3 nuts. So the last 3 turn will be for each the 3 nuts, and the same thing for the first one is the linear turn, quadratic turn, and cubic turn. And also, if you want to choose in this way, you can use another way instead of use the df is equal to 6. And how do we know this nuts value? So in this function, they decide put the nuts at the equal space. For example, in this case, we have 3 nuts, and we have therefore we have the 4 regions. 4 regions, which means that we can, if we have a equal space, so we put the nuts at the 25, 50, 75 percentile. So instead of you can choose the longer like this quantile and put the specific nuts is like this, and you can show the same results. So I just compare it with this is we choose the df is equal to 6, and you can see the coefficient will be like this. And if we choose the correspond to this, and you can see this coefficients, they will show the same, the same way. So, and the next thing, you also can use the quadratic splines. You just input your degree is equal to 2, and you can fit the quadratic spline, and this is the result. So the quadratic spline, in this case, we choose the df is equal to 6. So degree is 2, so we totally have the 4 nuts. So 6 minus 2 is equal to 4. So the last 4 will be the nuts. And this will be linear turn and quadratic turn. And also you can choose the same way, use the specific nuts, put into the 20, 40, 60, 80 percentile, and it will show the same result. Okay, so the next thing is the natural spline. We use the NS. The same way we can put the nuts at the specific values, and you can see. And in this way, we have 3 nuts. So the last 3 will be nuts, and the first is intercept, and this will be linear turns. Just reminder, the spline specific function, we have like this. First is the intercept, and second is the linear turn. So, and the other way, you can choose the 1 nuts. You can see they will show this only for the 1 nuts, and also you can plot the predict functions. They will show like this. And we also can plot this B-spline and natural spline together, and you will see like very different. And you can find out for the natural spline, in the very beginning and the very end, they will fit a linear path for this. So you will see the blue line will be linear in the first region and the last regions. And for the cubic spline, there will be the cubic turn. So there will be the more curvature for the first region and the last region. And then so you also can choose the DF number of the coefficients with the same thing. So if we choose the DF is equal to 4, and then we have the 3 knots, which is 4 minus 1 minus the intercept here. And intercept, we did not choose the, it's a 2, so its default is 4. So if the false, this intercept will 0. So 4 minus 1 minus 0 will be 3. So in this case, we have the 3 knots. And for the first thing is a near turn. This is for 3 knots. And also you can set up the specific percentile for specific value for the knots, and it will show the same result. And the next part will be the smoothing spline. And smooth spline is very easy. You need to put the X, which is the predictor and response, and put the algorithms, and you can fit. And you also can use the CV, which is the cross validations. It will be truth. That will show you the estimate algorithm. So in this case, we will have the 6.8 algorithm was enough for the smooth spline, not instead of the 16. And you also can plot it. This is a 2 algorithm choose the 16, and instead of choose the 6.8, it will be very similar. And so for the next thing will be, you can fit the game model with the 2 predictor. So the first thing, use the ln function. Right now we have the 2 predictor, which are the age and year. And I fit the difference for the BS, use the BS to fit the age, and NS fit the linear, and choose the algorithms. And then we can see the result. So this part will be B-spline. We choose the algorithm is 5, so totally have the 2 knots. And for the natural spline, DF is 4, so 4 minus 1, so they have the 3 knots. And each knot has you can see the estimate. And then we can plot for the each f function. So the first one is the BS versus your age, first predictor, and the second will be the natural spline versus the year, which is the second predictor. So, and this shows that for the first predictor, the response will be, the relationship between this will be like the quadratic, it's not linear. And for the predictor year, they will show kind of a linear trends. So you can see the summary results like this. And the second, it will be use the GAN package to fit the game model. So we just need to library GAN and use the GAN functions. And in this case, we only need to use the smooth spline. And they will show the result like this. Yeah, and if you can look into for the age, this smooth spline, their p-value is very low, so which means it's significant. But for the years, they did not significant because which means that you choose the dicophydence for is not significant. So maybe you can choose another dicophydence so we can plot it to see that. And we can find that is for the linear predictor list, there will be show the kind of linear term. So maybe dicophydence is choose one, that will be better. So and then I choose the one here, and you can see the summary result that will show here. If you choose the dicophydence is one, they will show significant. Yeah, and the next part will be the MGCV package. The same things, you also need to library MGCV package and use the same GM functions and choose the dicophydence for each predictor. And let's see the summary result. That will be the different from the GM functions. In MGCV packages, they will show your, let's call the estimated dicophydence. In this way, you can see that for the age, the estimated dicophydence was 3.8. That will be better. And for year, it choose the ones. So let's will tell you about how do you choose the dicophydence. And you also can just plot it. That will see like this. So we can find that the response versus the age, they will show the nonlinear trends, and but for the relationships between the response with the year, they will show the linear trend. And that's it. So does anyone has a question? Okay, so I think this is it. Thanks everyone.